Hello and welcome to another lecture of classical motion of a single particle. And here we simply continue our previous discussion on different features of motion under an attractive inverse square force field. Okay. So, I just said that we already know that the under an inverse square attractive force field the trajectory of a particle is given by simply this equation, which is geometrically the polar equation of a conic section. And we have already discussed that conic section can be broadly of three types: elliptic, parabolic and hyperbolic, and a fourth type if you want to include, that is the circular, but it is a special type of the elliptic orbit. Okay. And now the point is that we have already discussed something in the previous lecture. This is just to relate the total amount of energy. If the total amount of energy is positive or 0, then the system will, the particle will exhibit an unbounded motion with a parabolic or a hyperbolic orbit. If the total energy is negative, then the particle will show a bounded motion with an elliptic or a special case a circular orbit. Okay. We then also said that the eccentricity of the conic section, which is given by small e, will be related to the constants of motion in this way: root over 1 plus 2 capital E L square by m k square. Here E is the total mechanical energy, and we also said that E is greater than or equal to 0. Okay. That is the definition of a conic section here, and here we will say that, I mean, that is following the definition of a conic section here, because E is actually should be always at least positive or 0. Okay. It cannot be negative. Now, I am just taking this equation once again, which we can also show from Binet equation or any other correct way, that r is equal to p by 1 plus epsilon or E cos theta. E is the eccentricity, p is the semilatus rectum, and p and E, they are simply related to the constants of motion. So, they are also constants. So, I can write the expression, exact expression of E to be root over 1 plus 2 E L square by m k square. And if you remember also, I can write the expression for P is equal to m h square by k. Just writing that h as L by m, I can also write this is L square by m k. Okay. So, you see that these two are also two geometric constants for my system, for the motion of the particle. Okay. Now, I just want to have the estimation of that if the particle, let us say, is travelling in such a way or is moving in such a way that the particle is having some r mean and r max. Okay. So, I am just saying that okay, right from this expression can we simply estimate, find an expression for those r mean and r max. So, p and E, since they are constants, the only variable here is the theta. And you know that, so simply from this expression, this is quite easy to check that r will have its minimum value when this part will have the maximum value, and when this is maximum, that means the cos theta will also have a maximum value. What is the maximum value for cos theta? That is plus 1, and that is why r mean will simply be equal to p by 1 plus E. Cos theta is equal to 1. I can go for the r max. Now, r max is equal to p by 1, then cos theta should be minimum, is the case where I will have the r max, the same thing. Okay. This is just the opposite of this case. So, this will be minus 1 and I will have minus E. Okay. Now, you see a very funny and interesting conclusion from that is, whenever your system has a, so now I from my coordinate geometry knowledge, I know that circle, ellipse, and then the other two is parabola and hyperbola. I know their eccentricities. For circle, eccentricity is 0. That means R mean is equal to R max, and what is that? Is nothing but equal to P, because E is 0. Okay. And you will have a circle. Okay. So, for circle you will have a bounded motion where the R mean and the R max is both are equal to P, and you have only one turning point, and that is the, because this is the local minimum in the effective potential well. Okay. For ellipse, E we know from coordinate geometry should be, for a perfect ellipse which is not a circle, should be varying from 0 to 1. So, it should be a proper fraction positive. Okay. And that is why this E will be less than 1. Okay. And that is why you will see that R mean will be equal to P by 1 plus E, and which now, since this is a positive quantity, 1 plus E will be greater than 1. So, this will be something which is P by some chi which is greater than 1, and this chi is actually greater than 1. So, you can actually write that this should be less than P. Okay. Now, again R max, which is P by 1 minus E, same thing, E is positive. So, this should be less than 1. So, this fraction will be actually greater than P. Okay. But both of them will be finite, and that is why you have a bounded motion, although R mean is not equal to R max. Okay. For parabola, what happens? We know again from coordinate geometry E is exactly equal to 1. Okay. The eccentricity is exactly equal to 1. Now, what happens if you have this? Then this is R mean is equal to P by 2, but R max is equal to already infinity. Okay. So, you have R mean P by 2 and R max is infinity. So, you have unbounded motion. Again you see the results are so consistent with each other, unbounded motion. So, just for E is equal to 1. Okay. Now, you see I am coming to that in a second, and for hyperbola finally you will have E less than I would say, sorry, correct myself, E greater than 1. Okay. And for that what happens? This one is still, I mean, is finite, but this one R max is actually less than 0, which is not possible. So, this is absurd. Okay. And that is why this is also unbounded motion. Okay. Now, I can tell you another important thing, that what happens in circle, ellipse, parabola and hyperbola in terms of energy. So, when we now know the relation between E and capital E. So, E square is equal to 1 plus 2 E L square by m k square. If I say E is equal to 0, this is equal to 0, then I know that 2 E L square by m k square, okay, plus 1 is equal to 0, that means this is equal to minus 1, and your E is equal to simply minus m k square by 2 L square, which is the, if you remember, this is the case for the minimum potential energy, and your total energy is simply is given by this one. Okay. So, your E is negative. For ellipse, once again I can just check here, you see that already we know that for closed trajectories your E will be negative. I am again cross checking here from these aspects as well. So, if your E square is if your E is less than 1, then E square will also be less than 1, and then your 2 E L square m k square I can write for ellipse, just for ellipse, E square is also less than 1. So, I can simply write 2EL square by mk square is equal to E square minus 1, which is less than 0, and these all are positive. So, only possibility is E is less than 0. So, here also E is less than 0. For when E is equal to 1, what happens? E is equal to 1. So, you have both sides 1. So, if it is 1, then 1 and 1 they will go away. So, your whole thing, this thing will be equal to 0. It is for parabola. Okay? And then you can say that means this cannot be 0, L, M and K they cannot be 0. So, E is 0. So, for a parabolic orbit, the interesting thing is the total mechanical energy always vanishes. Okay. Then finally, the hyperbola. Okay. A parabolic orbit, the total mechanical energy vanishes only for when we are considering attractive inverse square law. Okay. For other laws there can be different situations and different conclusions. Okay. Now hyperbola, finally. Hyperbola is E is greater than 1. So, this quantity is greater than 1. So, E square minus 1 will be some positive quantity, and so 2EL square by mk square, this fraction will be positive, L square mk by mk square positive. So, E will be positive. So, again E will be positive. So, you see from this analysis also again we have cross checked this energy and the nature of the trajectories. Okay. So, what is the immediate conclusion? That when your energy to total energy is negative, that means that the potential energy part, the true potential energy part actually dominates the true kinetic energy part. Okay. And when they are exactly equal to 0, that means the true potential energy exactly equals to the true kinetic energy, and when the trajectory is hyperbolic, then actually the kinetic energy, true kinetic energy, okay, like dominates over the true potential energy. Okay. Because if you remember in the energy expression, okay, both the kinetic energy terms, these two terms, these and these, both of them are actually positive. So, if the total energy should be positive, then this part should win. If this is 0, then this part should exactly be counterbalanced by this, and if finally this is negative, then this part should win. Okay. Now, you think the real situation when we are talking about the planetary motions, all the planets are moving in elliptic orbits. Okay. As we know from our experience, okay, they are moving always elliptic or whatever, like a little bit circular elliptic, whatever. I mean, if you even forget about this debate, whether this is elliptic or elliptic, I mean nearly circular, okay, whatever, but they are elliptic of course, as far as we know that they are inverse square attractive law, and they are always moving in the closed orbit. There are some deviations from a proper closed orbit sometimes, but that we neglect for the time being for this course. If you just take this conclusion, then the immediate inference is that for a planetary motion, the potential energy, the true potential energy, the attractive potential energy is actually winning over the kinetic energy. Whereas, if you now think in the solar system, you have several other members, for example, a comet, which comes and then the comet vanishes forever. Okay. It can actually have a 0 or a positive total mechanical energy, where the kinetic energy dominates over the potential energy. Finally, a very interesting point, some comets are periodically, I mean observable. Okay. So, you can see them in an interval of several years, and for those basically again you have to understand that they are actually somehow moving in a closed trajectory. So, although they are comets, their total energy is negative, otherwise there is no, I mean you cannot see them once again. Okay. Now, coming to a little bit more analysis. So, what I can do directly just to talk about, so you now know that under which conditions the trajectory will be ellipse, when it will be circular, when it will be parabola, and when it will be hyperbola. But at least one thing we have to now we can discuss different situations already we know under which condition of energy the trajectory will be a circle, under which condition of energy the trajectory will be an ellipse, where the trajectory will be a parabola or a hyperbola. Now, by case to case we will try to analyze in more detail whether we can actually find the equations in our familiar Cartesian form of those conic sections. Okay. So, I will do it part for you and you are asked to do the rest of that. So, just if I take r is equal to p over 1 plus e cos theta, then I can say r plus e r cos theta is equal to p, okay, and try to a little bit, okay, yeah. Then I can simply write. So, what is my r in Cartesian coordinate? This is root over x square plus y square plus e, r cos theta is a x is equal to p, another constant. So, I can just take this one on the one side and p minus e x on the other side. I take the square of both sides and I take x square plus y square, I square them, then they will give me p square minus 2 p e x plus e square x square. If you rearrange, you will have a very friendly form, x square 1 minus e square plus 2 p e x plus y square is equal to p square. So, this is the familiar Cartesian form of the conic sections. Now, we do case by case. So, 1, when e is 0, we know that this term will be 0, this term will be 0. So, we will have x square plus y square is equal to p square. So, it will give me a circle of radius p, and that is exactly also can be verified from this condition that it will have a trajectory, closed trajectory, where both r min and r max is equal to p. So, only one are possible and that is p, and that is the exactly consistent with the circle equation of this circle. Okay. So, circle. When I will have this, I can also try to find the equation of the circle from that, and you know that is completely doable, and the radius will simply be p is equal to, since we know the for semi-lattice rectum this is given by L square by m k. So, it will be a radius of circle L square by m k, and what is this? If you remember, in one of the previous lectures we said this is the radius of the circle, okay, for minimum effective potential energy. Case number 2, when your E is a proper fraction, but positive, okay, then what you can do, that this thing is not 1, but this is something which is positive quantity. This is also positive. How to write that thing? So, we can simply write it in a stylish way. So, we just write over here that I have this thing, and then I can say the equation can be written like this: x square plus 2 p e x by 1 minus e square. I am just dividing everything by 1 minus e square, which is a positive quantity here for this case where e is less than 1, plus y square by 1 minus e square, and then the right hand side I write in a smart way. I just write p square as p square times 1 minus e square by 1 minus e square whole square plus p square e square by 1 minus e square whole square. Okay. If you just add them up, you will simply see that just a minute, let me just check. I can write this, yes, Yeah, I can write actually, then I have to add something over here, that is this quantity. Yeah, I actually have to add over here this one as well, 1 minus e square whole square. Yeah, so I just write this left hand side over here, this left hand side, the entire left hand side as this terms, and the right hand side I wrote in this way. Okay. Here in both sides I actually have added this term, p square e square by 1 minus e square whole square. Okay. If you simply just want to cross check, you just cross check and you let me know that, I mean, whether it works or not. Okay. So, basically what happens that you are dividing everything by first 1 minus e square. So, this will gives you everything like this, and in the right hand side you will have a p square by 1 minus e square, and then you just multiply 1 minus e square in both numerator and denominator, then you will have this term, and then in both right hand and left hand and right hand side you add this term and this term. Okay. You just add equally. Okay. What is the advantage of this thing is that finally you write those equations as x plus p e over 1 minus e square whole square by a square plus y square by b square is equal to 1. Okay. Where your a is given by p by 1 minus e square and b is given by p by root over 1 minus e square. Okay. And both of them are greater than 0. So, this will be greater than 0, this will also be greater than 0. So, they are not equal here, they will be of course equal if e is 0. So, this is the case for an ellipse, case for an ellipse. Non-circular, I just mentioned that, non-circular. Okay. If you follow the formula for p and e over here and here, then you will finally get, we can write a is equal to L square by m k, that is p, by then 1 minus e square is nothing but 2 mod of e L square by m k square. Mod of e means the positive value of e. Okay. If you take this, you will have equal to k by, just after this cancellations in the numerator and denominator, k by 2 mod e, and b will be equal to, in the same way you do the same steps, you follow the same steps, you will have root over L by root over 2 m mod of e. Okay. I encourage you to do those calculations once again right from these expressions and using their using the expression of p and e separately to reach reach those expressions. Okay. So, this will be an ellipse, okay, with semi major axis as A and semi minor axis as B and center at minus P e by 1 minus e square, just this one, the negative of that, comma 0, because there is nothing in the y coordinate. Okay. This is once again the revision of the coordinate geometry. The task for you will be to check, I can also do the case for parabola, that is also not very difficult. So, E is equal to 1 and that is the total energy is equal to 0. So, you will actually see the main equation, this parent equation reduces to this, y square is equal to p square minus 2 p x, which is nothing but minus 2 p x minus p by 2. Okay. And if you have this, then this is once again a parabola with its vertex, I am sorry for repeating problem, yeah, vertex at p by 2 0 and focus at origin 0 0. Okay. So, you can also check this from your coordinate geometry book. Okay. Finally, the task for you, do the case for E greater than 1. Okay. I will be wrapping up this lecture by finally stating the 3 famous laws of Kepler, and for that we just need the knowledge which we have already discussed, that is mostly. So, Kepler gave his law, Johann Kepler gave his law for analyzing or for modeling, describing the planetary motions, and for planetary motions the first law of Kepler gave. So, Kepler's law for planetary motion. So, we understand that Kepler at that point he did not have all the analytical tools at hand, but what he meant that this is the analysis some laws for the motion under an attractive inverse square law. So, nowadays if we just relate this to our knowledge, attractive inverse square law with negative E, right. So, that is the case for planetary motions. So, the first he said that, okay, I am just writing this, yeah. So, the first law said the planets move in elliptic orbits, which we have now shown analytically, elliptic orbits with the sun at one of its foci. There are 2 focal points of an ellipse, and so the point is that the first law simply said that if a planet moves in an elliptic orbits, let us say like this, if the planet moves like that, then sun should be here. So, that was his law. Okay. Now, it is I give you a week for thinking how can, from the analysis which we have done, we have now given the equation for the ellipse, you see, how can you actually think of the sun's position under this framework. Can you do that? Okay. That is a good good exercise to think. So, here it is a sun and there is a planet. So, that was the first law. So, we have actually shown the first thing, that the elliptic orbits, okay, that is completely consistent with our knowledge of the nature of the trajectory under negative total energy, which says that the motion will be bounded, and that is why you will have an elliptic orbit, because the orbit must be a conic section. Okay. And the second law again simply said that the second law, second law simply said the radius vector of a planet sweeps out equal amount of area in equal time. Okay. Or you can say equal amount of area in equal time, or sweeps out area at a constant rate. that means that if the sun is here and the particle is moving like in a trajectory like this. So, if the initial position vector was here and the final was here, then I can say this is r, and this is, I mean, this is just, I mean, after some considerable time, if I just say immediately after, when it will have some r prime, which you can say r prime is nothing but r plus dr, and this dr vector basically is this vector which is almost perpendicular to that, and actually should be perpendicular because this is along the tangent of this curve. So, this is the direction of the dr here. So, then you can say that d of A, which is the area vector modulus per unit time. So, the change of the area vector. So, area vector is the area subtended by this planet. Okay. So, let us say in dt time the area subtended is this part, the small triangle, okay, and that is d of mod of area vector. I know from my knowledge of vector algebra, this is nothing but half r cross dr by dt. So, this is the small triangle subtended by r and dr, and they are almost, they are perpendicular actually. So, that is why you can simply write there nothing but half ddt of, so r dr. So, that should be actually, so r cross dr will be the just the cross product in of two vectors at 90 degrees. So, this will be simply r dr, and what is this dr? If you remember, just for this purpose, if there is an angle theta. So, what is that dr? Dr is nothing but almost, dr is almost, or r d theta, because this is, sorry, this is an angle, small angle d theta. So, it will be r d theta. So, finally, your thing will be, so instead of writing it like this, I can simply write this as r d theta dt. Okay. And this is the r, I mean r d theta is just the dr part, and there will be another r multiplied. So, it will be simply like this, and you will have half r square theta dot, and what is this? This is nothing but h by 2. So, which is a constant of motion in any central force, and that is why this is completely understandable why second law of Kepler must be true. Now, for Kepler's second law, you see that this is a general conclusion which is true for any central force, whereas the first law is only true for planetary motion. So, for the first law needs the force law to be inverse square, attractive, and the total mechanical energy to be negative, whereas the second law is much more general. Okay. But since the planetary motions are also, I mean, under a force which is central, and then I mean any conclusion can also be interpolated. So, at that time Kepler did not have a detailed didactic method for I mean to reach all these conclusions step by step. That is why he just postulated those as laws. The third one is the third law of Kepler is also very special for elliptic orbits. Third law of Kepler. Yeah. So, it simply says that okay, since we have used this thing already, dA dt is equal to half r square theta dot, which is nothing but h by 2 or L by 2m, the same thing, I can actually write the A, which is the mod of the area vector, to be equal to L by 2m times t. Okay. Since this is constant, I can simply just say, I mean this t is the time. Okay. So, I can write like this t. Okay. Yeah, I can integrate and I can say when at t is equal to 0 the area was 0. So, I can have this simply linear relation. Now, for an ellipse, this A is nothing but pi times A times B, where A is the semi major axis, B is the semi minor axis. Okay. So, I can write that pi A B will be equal to L by 2 m times T, okay, and that is why this T will be 2 m pi A B by L. Okay. I will do something which is also very interesting here. I will use this A is equal to what I just said, K by 2 modulus of E, and B is equal to L by root over, let me just check once expressions, yeah, K by 2 modulus of E and B is right, yes, L by root 2 m modulus of E. And if you do simply this, you will actually see B square will be equal to L square by 2 m modulus of E, and then you just use this relation to simply write B square is nothing but equal to L square times 2A by mk. Okay. Now, you see there is a square, I mean there is a nonlinear relationship between A and B here. Okay. I simply use that one over here just to write 2 m by L pi, I will write A as A, but B I can simply use this relation and I can say that okay, then B will simply be equal to L by root 2A by root mk. I can write. I can do the same thing over here. I can simply write root 2 L square by mk, and then it will be A to the half. Okay. All the other quantities over here, they are just the constant, and it will simply be equal to some constant k0 times A to the power 3 by 2. And that is why you see that, okay. So, of course, here you see there is a point that A, whenever you are talking about the A to be the area of the total ellipse, then of course, you can say my T is nothing but the time period which is equal to the total T, capital T. Okay. I can call that as capital T as well, and I can say okay, then my T is equal to K0 A to the power 3 by 2, and finally, I say T square proportional to A to the power 3. Clear? So, this is the Kepler's third law. Okay. And remember, although A and B both are, I mean one is semi major axis and one is semi minor axis. So, the dependence of T on the B, which is the semi minor axis, is not the same, because A and B, they are not linearly related. What will be that dependence? For example, if I say T alpha proportional to B beta, then what will be alpha and beta? That is you to think. Okay. With that, I wrap this lecture up, and you tell me that what will be the cases, what will be the case for or the reduction for the Kepler's third law, if we simply think of a circle. Okay. It is simply something you can easily calculate, or you have to do some non-trivial calculation. Circle means A is equal to B. Okay. Thank you very much.